Hello, this podcast is an introduction to forces. We're going to look at what is a force, how do we label forces, what different types of forces are there. We're going to talk about forces and motion. We're also going to learn about inertia and Newton's first law of motion. We're going to learn how to draw force diagrams, and lastly learn about component forces and how to draw them on force diagrams. A force is an interaction between two objects. It's a vector quantity, so that means it has both magnitude and direction, just like displacement, velocity, and acceleration. It is a push or pull, so all forces will either be a push or a pull. In this picture we have a cat sitting on the rug. And of course the cat is motionless, and there's two forces at play. First, we have the earth pulling down on the cat, so the two objects involved in this force are the earth and the cat. The other force is we know that the rug is pushing up on the cat, so this force is an interaction between the rug and the cat. Here we have a skydiver, and we've got two forces acting in this picture. The first one is the force of gravity pulling down on the skydiver, and that's an interaction between the earth, because it's the earth's gravity, and the other object is the skydiver. There's also a force acting to slow down the skydiver, and that is the interaction between the air and the parachute, and the air is pushing up on the parachute. We need to have a way to identify forces, and we do that by creating labels. Here's the general template we're going to use. We're going to use a capital F, stands for force. Then as subscript, we're going to have the type of force, comma, the object exerting the force, then an arrow, and the object that's receiving or feeling the force. Remember, a force is an interaction between two objects, and we must list both of the objects in the label as well as what type of force it is. So let's look at some examples. So in the previous slide we had the Earth's gravity pulling down on the cat, and that label would be F, gravity, because gravity is the type of force, Earth, because that's what's exerting the gravity force, the arrow, and the cat, because the cat is feeling the gravity force. The other force in that sketch was the rug pushing up on the cat, and that force starts with capital F. It's a normal force, and we'll talk more about that later. And the force exerting, and the object exerting the force is the rug, and the object receiving or feeling the force is the cat. Moving on to the skydiver picture, we had the Earth's gravity pulling the skydiver down, and that label would be F, and subscript gravity, Earth exerting the force on the skydiver. And finally, the air pushing up on the parachute, that's a force. It's a drag force, and it's the air pushing up on the parachute. So this is how we label our forces, and it's just a way of identifying them. Now let's talk about these different types of forces. There are many forces, but we're going to study or talk about some of the more common ones, especially the ones we'll encounter in this course. First, under the column of perpendicular, we have a normal force, and this is a push force between two solid surfaces, such as you're sitting in your chair, and so the chair is pushing up on you. Buoyancy is the floating push force of a gas or a liquid on a solid. So this is similar to the normal force, except instead of a solid surface pushing up, it is a liquid or gas pushing up. An example would be a boat floating on the water. The water would be pushing up on the boat, or if we had a helium balloon floating in the room, it would be the air pushing up on the balloon. The other type of perpendicular force is a lift force, and this is a steering push of a gas or liquid on a solid. For instance, if we're steering a boat and we would turn the steering wheel and that turns a rudder that's in the water, and the force of the water pushing on that rudder will steer the boat. If we're talking about a gas like air, airplanes, Their wings create a lift force that allows them to go up into the sky, stay there, and steer. And so it's the air pushing on the wings of the airplane that cause the lift force. And these fall under the perpendicular column because these forces can only act perpendicular to the two surfaces. Next, we have parallel forces, and we have friction. This is the force between two solid surfaces that hinders motion. Similarly, we have attraction force. These are two solid surfaces that aid in motion. So these two are very similar. An example of friction would be when you apply the brakes to your car. The force between your car tires and the road is acting to hinder the motion of the car, so we would call that friction. On the other hand, when you step on the gas pedal to pull away from an intersection, the force between your car tires and the road is aiding the motion, causing the car to speed up, so we would call it traction. Then we have two similar forces, drag and thrust, that involve a liquid or a gas. So for instance, when you're driving the boat through the water and the water is acting to slow down, the boat, we would call that a drag force. Similarly, if you throw a football in the air and the air acts to slow down the football, that's a drag force. Thrust is just the opposite. This would be a force that doesn't hinder the motion, but a force that aids the motion. For example, with boats, you have an engine that turns the propeller, and the water pushes on the propeller to make the boat speed up. And this would be the case of a thrust force, or liquid. In terms of another thrust force, if you have jet engines on an airplane or rocket engines on a spaceship, the gases exhausting out of the jet engine or the rocket engine are pushing the plane or rocket forward, causing it to speed up and aid motion. So again, drag force hinders motion, and it's a liquid or gas hindering the motion of an object. Thrust aids the motion of an object, and it's the liquid or gas that is aiding in the motion. These are under the parallel column because in these instances the force acts parallel to the two surfaces. And finally, we have two miscellaneous forces. That means that they can be parallel, they can be perpendicular, or they can be anywhere in between. And we have gravity, and this is a non-contact pull force between two objects with mass. By non-contact, we mean that the objects don't have to be touching each other. For instance, we know gravity is non-contact because if you throw a ball up in the air, the ball is not in contact with the earth, yet it's the earth's gravity that is acting on it. And one important thing about gravity always acts to pull an object to the center of the earth. Another common type of miscellaneous force we have is a tension force, and this is a pull force between two objects. We typically think of it as a rope or chain pulling an object, but it also could be a solid steel rod or any other object. Or for instance, if you stick out your arm to help pull a friend up off the ground, your arm is exerting a tension force on your friend. Now, this is by no means a comprehensive list of forces, but these are the ones that we're going to use most often. Lastly, I just want to point out, you'll notice that there's an underline under some of the beginning letters, and that's because you can abbreviate these forces using those symbols. For instance, if you want to abbreviate the force of gravity, instead of writing force subscript gravity, you can write force subscript g. Okay, now that we know the different types of forces, let's talk about how forces affect motion. And there's two general classifications of forces. We have balanced forces, and these are two forces of equal strength but acting in the opposite direction. So notice on this box, we have a 5 Newton force. Newtons is just the way that we measure the strength of the force. We have a 5 Newton force pulling to the right, and we have a 5 Newton force pulling to the left. In this case, the forces are balanced. They're equal to each other and opposite in direction. We have unbalanced forces, and those are two forces of unequal strength acting on an object. They may or may not be in the exact opposite directions. In this case they are, but they don't have to be. So we have a 10 Newton force pulling to the right, and we have a 5 Newton force pulling to the left. They're unequal in strength, so these are unbalanced forces. And this is important because this tells us the type of motion. Forces cause objects to move. It's one of the most important concepts to remember in this course. Balanced forces cause no motion or constant velocity motion. So if this box were sitting on the floor not moving and we applied a 5 Newton force to the left and a 5 Newton force to the right, it would be motionless. It was at rest, it'll stay at rest. However, if the box was already moving along the floor, let's say at 2 meters per second, and we applied a 5 Newton force to the left and a 5 Newton force to the right, it would continue to keep moving at a constant velocity of 2 meters per second. So important to remember, balanced forces cause no motion or constant velocity motion. Unbalanced forces cause an object to speed up, slow down, or change direction. Don't worry too much about this last one. We're going to get to that in a unit later in the course. But if we look here at this box, if it's at rest and we all of a sudden start pulling on it to the right with 10 newtons and pull to the left with 5 newtons, the object is going to speed up to the right. And as long as the forces are unbalanced, with the stronger force being to the right, the object is going to keep speeding up until we either have a greater force going to the left, in which case it'll slow down, or if we have balanced forces, it'll maintain a constant velocity at whatever speed it was at when the forces became balanced. Let's talk about inertia and Newton's first law of motion. Inertia is a quantity that measures how resistant an object is to changing its motion. Mass is a good way to measure an object's inertia. So heavier objects, objects with more mass, have more inertia because it's harder to get them moving, and if they're moving, it's harder to stop them from moving. Lighter objects have less mass and they have less inertia because it's easier to get them moving, and if they're already moving, it's easier to stop them from moving. So let's take a look at which one has more inertia, the cart in figure A or the cart in figure B. Well, it's the cart in figure A because it has a total of 34 kilograms of mass, whereas figure B only has 12 kilograms of mass. And of course we know it'll take more effort, more force to get this cart moving, and if it's already moving, it'll take more effort to get it to stop. Let's move on and talk about Newton's first law of motion, which is also known as the law of inertia. So Newton's first law says an object at rest will stay at rest unless acted on by an external net force, and an object in motion will stay in motion unless acted on by an external net force. So for instance, the book that's sitting on your desk, we know that if you don't push it or something else doesn't push it or pull it, it's just going to stay there. That's what this first part means. It's going to stay there at rest unless acted on by an external net force. The last one here, or the second one, is a little harder to visualize, but if an object's moving, it will stay in motion unless acted on by a net external force. So for instance, if we take a ball and we let it roll down the floor, it will keep moving until an external net force acts on it. Now the reason I say this is hard to visualize is we know if we roll the ball, we know if we let it roll long enough, it's going to come to a stop. But that's because there's friction. So friction is that external force acting to slow it down. If we didn't have friction, we know that the ball would roll further. And in outer space, there is no friction. So things in motion in outer space just keep moving unless there's an outside force acting on it. So let's move on and talk about force diagrams. Force diagrams are a way to represent the forces acting on an object. In this case, we're going to draw a force diagram on the log, and it's best to start with an XY axis. That's what these dotted lines represent. So the first step is to identify the object and shrink it to a point. So we're doing the log, and we're going to shrink it to a point, and we're going to stick that dot at the origin. Next, we want to draw all the forces acting on the object, and to do this we're going to use arrows to represent the forces. The arrows are going to point in the direction the force is acting, and longer arrows mean stronger forces, and of course shorter arrows mean weaker forces. So we know there's a force pulling down towards the center of Earth. We also know that the ground is pushing up on the log. We can see from this picture that there's a force, the rope, pulling the log to the right, and we know that the ground is causing friction, hindering that motion, so it is pushing to the left. Next, we want to label all forces using our force label template. So capital F for force, the type of force, it's a gravity force, and it's Earth's gravity pulling the log towards the center of the Earth. Now let's look at this force. It's a normal force because it's two solid surfaces, the ground and the ground is pushing on the log. Next, this force acting to the right is a tension force because the rope is pulling the log, and tension is a pull force. Finally, we have the friction force because the ground is pushing parallel to the log and it's hindering the motion, so that makes it a friction force. Notice the ground is exerting two types of force. It's exerting a push force perpendicular to the ground, that's called the normal force, and it's exerting a push force parallel to the ground, and that's called a friction force. We do not want to draw forces that the object exerts on its surroundings. For instance, we know that the log is pushing down on the ground, but we don't want to show that force. We're only interested in the forces acting on the log. Similarly, we know that the log is pulling on the rope, but we're doing the force diagram on the log, so we're not showing that force that the log exerts on the rope. And finally, we want to use equality marks to identify pairs of balanced forces. Now let's look at these. First, horizontally, we know that these two forces are balanced because the log and the tractor are moving at a constant velocity, so we need to have balanced forces. If we look in the vertical direction, we know that vertically the log's not moving. It's moving horizontally, but it's not moving up and down. So we know that the gravity force and the normal force are balanced, so we need to use equality marks. So these slash marks or tick marks are called equality marks. Notice I used a double set for the vertical forces because while they're equal to each other, we don't know that they're equal to the horizontal forces. In fact, I'm pretty sure they aren't. So if we had just used single slash marks all around, we would be saying all four forces were equal to each other, and that's not the case. These two are equal to each other, so we use single slash marks, and these two are equal to each other, so we have to use a different unique set of equality marks, so we use double slashes. If we had a third pair of forces that were equal to each other, we would use triple slashes. Finally, let's move on and talk about component forces. So many forces don't act straight up and down or perfectly sideways. In this sketch over here, that's the case with this rope. Notice that the person is pulling the rope up and to the right, so it's not perfectly horizontal and it's not perfectly vertical. When that happens, the force is acting both up and right, and we can break the force into its component forces. Component just means parts. So we're going to break this force that's going up and to the right, we can break it into its horizontal component. That's the component that's acting sideways, and we can break it into a component that's acting straight up and down. And so when we do this, this single force that's acting up and to the right creates the same type of motion as if we had one force acting straight up and another force acting horizontally to the right. Let's draw the force diagram for this sled. So the first step is just like we did in the previous slide. We're going to draw and label all the forces acting on the object. So we have the down force acting on the sled, and that's the force of gravity. I'm using abbreviations now just to keep these labels smaller. Force of gravity, the earth acting on the sled. We have a vertical force, and we know that's the normal force of the ground pushing up on the sled. We have the rope pulling the sled, and notice the rope is going up and to the right, and that's a tension force because it's a pull force, the rope acting on the sled. And we also know that we have a force acting horizontally to the left, and that's the friction force. That is the ground acting or pushing to the left on the sled. Next, we want to identify forces that aren't on the x or y axis. Well, you can see that these three forces are on the x and y axis. They're perfectly vertical or horizontal, but the tension force doesn't lie on either axis. So in that case, we need to draw and label their horizontal and vertical components. So to do this, well, I'm going to start with the horizontal component, and I'm going to draw the arrow on the x-axis, and I'm going to draw it as far to the right as this force goes to the right. Notice if I draw a line straight down from the tip of the tension force, it comes this far on the x-axis. So that indicates how far my arrow should go for the horizontal component. This indicates how strong the horizontal component of this tension force is. And for my label, I'm just going to call it F sub Tx. I don't have to put the rope and the sled in anymore because I know that this is the x component of this tension force, and it involves the same two objects, the rope and the sled. Next, I have to draw the vertical component, and I'm going to draw the arrow up on the y-axis, and notice that I am drawing it as far up as the tension force goes. So the tension force goes this far up on the y-axis, so that's how far I'm going to draw this vertical component, and I'm going to label it F sub Ty. Finally, I'm going to use equality marks to identify pairs of balanced forces. Now, this sled is moving at constant velocity, so I know these horizontal forces need to be balanced, so I'm going to go ahead and put in my equality marks to show that the x component of the tension force is balanced with the friction force. That means that these two forces are equal in strength, they're just pointing in opposite directions. Now the sled is not moving up or down, so vertically it's motionless. That means that the vertical forces pointing up have to be balanced by the vertical forces pointing down. However, I'm not going to use equality marks because I have two forces acting up on the sled, the normal force and the y component of the tension force. So those two added together equal the strength of the gravity force pulling down on the sled. But because these two added to each other equal this, neither of these forces are equal to this one, so I'm not going to use equality marks. So you can have balanced forces where two forces acting in one direction balance out a single force acting in the other direction. It's just in that case, it's not a pair of forces that are balanced, it's a triplet of forces, and you only use equality marks to identify pairs of balanced forces. Finally, let's take a look at how we handle objects that are on inclined surfaces and the role component forces play. Objects on inclined surfaces are going to move parallel to the surface. Therefore, we need to rotate the x and y axes so that the x-axis is parallel to the inclined surface and the y-axis is perpendicular to it. In terms of forces, gravity acts straight down. It does not act on the y-axis. And of course, its x component is going to be parallel to the surface on the x-axis, and its y component is going to be perpendicular to the surface on the y-axis. The normal force is perpendicular to the surface, and it balances the y component of the gravity force. Other forces such as friction, traction, tension, etc. are parallel to the surface, and they are going to either aid or hinder the motion. In this instance, I showed these forces acting uphill, but they can also act downhill. The x component of gravity, however, will always act downhill. And finally, the x and y components are also known as the parallel and perpendicular components. Well, this wraps up our lesson on forces, force diagrams, Newton's first law of motion, and component forces. I hope this helped, and have a good day.